We are working with transformational geometry, which is the movement of objects on a coordinate plane. Now, these are rigid movements, so the objects do not change size or shape. So today we're looking at reflections. And reflections are just like when we look in a mirror, it's a mirror image. But the one thing you have to remember on a reflection is the image always flips. So if I started here and I looked through this line, its reflection would be the opposite. And this line is called a line of reflection. So every object that we're going to work with today is going to be flipping. Now, we also have rules for the flip, but it depends over which axis on the coordinate plane that we're flipping. We have an option. We could flip over the x-axis, so I could go from this position down to this position, or I could flip on the y-axis where I go from this position to this position. They have to tell us which axis is going to be our line of reflection, which means that's the line that we're going to flip over. So let's say that we're going to flip over the x-axis. Well, the rule for this is really easy. If I am given an original figure and they say you're going to flip that figure over the x-axis, that's all they have to tell us. And I know when I flip over the x remains the same, but the y is going to go opposite. I just memorized that rule. So if I were given these original ordered pairs, A is 1, -2, B is 3, -1, and C is 4, -4, and I go and I graph that, I'm here. I'm going to flip over that x-axis. So notice my x values are not changing at all. It's only the y values that are changing because I'm going from the negative y values to the positive y values. So all I simply do is I keep my x the same, 1, 3, and 4 remain the same, and whatever my y was, I just go to the opposite. So -2 became 2, -1 became 1, -4 became 4, and that accomplished my flip. Now check the flip. Did it go opposite? Well, A, B, B, C, C, it absolutely went opposite. But sometimes they don't want us to go over the x-axis. Sometimes they want us to go over the y-axis. So if that's the case, then it's the opposite rule. So I'm given my original, my x is going to go opposite, my y is going to stay the same. So if I had these pairs, -5, -1, B is -4, 3, C is 0, 2, here's my original figure. I'm going to flip it over that y-axis. So we can see that the y's are going to stay the same. I'm not moving on that y-axis. What I'm moving on is I'm moving on the x-axis. So my x's are going to go to the opposite. So -5 became 5, -4 became 4, 0, it doesn't have an opposite, we just keep it as 0. But my y's stayed the same, -1, -1, 3, 3, 2, 2. When I go to graph that, I can see that it's exactly in the same position along my y, but it's my b's that have been reversed. So reflections are really easy. You just have to think about what's happening when you're going over the x-axis versus the y-axis, but we're really just dealing with opposites. The last thing we're going to talk about is we're going to talk about rotational symmetry. Now, rotational means to turn. So we are turning objects, and when we talk about symmetry, it means that one side exactly fits on the other side, as if they were mirrored images. And that's why we have it with this reflection. Everything we're talking about is a mirror image. So when we go and do rotational symmetry with regular polygons, so that means all the side lengths are the same measure, all the angles are the same measure, all we have to do is count the number of angles they have, and that tells us exactly the number of lines of symmetry or rotational symmetry they have. The reason why is because every time we turn the object, it's exactly the same as what it looked like before the turn. So if I have a regular triangle, it has 3 angles, therefore 3 lines of symmetry. If I have a regular square, 4 angles, 4 lines of symmetry. A regular pentagon, 5 angles, therefore 5 lines of symmetry. Regular hexagon, 6 angles, therefore 6 lines of symmetry. That's all we have to remember. Now, it only works with regular polygons. You cannot do it with irregular. So a rectangle is an irregular polygon. A rectangle does not follow this rule because 2 sides are different lengths than the other 2 sides. And when I go and I actually fold it, there's only 2 ways I can fold it where one side exactly fits on the other. So always rotational symmetry. This kind of shortcut rule only applies with regular polygons. If you ever are working with irregular polygons, you literally have to do the folds to see if they actually fit on top of each other. So have fun with reflections. It's pretty easy today. Good luck.